Okay, hi everybody. Welcome to another meeting of the New England Dynamics and Number Theory seminar. Uh, we chose this time period so that people from the West Coast could join, and now we have a rare occasion of somebody from out there moving to New England virtually. So, Han, if you're here, could you do us a favor and introduce the speaker?
Oh, yeah, sure. So welcome everybody. So today our speaker is Zuo Lin from UC Berkeley, and he will tell us about something about polynomial effective equidistribution for some higher dimensional unipotent subgroups. Now, Zuo, the floor is yours.
Okay, thanks for the introduction, and I would like to thank the organizers for inviting me. It's a great opportunity to speak in this seminar. And oh, just before I start, since I cannot see the Zoom chat room, and so if there's any questions or comments or remarks, just feel free to interrupt me and yeah, and say it. Okay, so let me start. So my title for today's talk is Polynomial Effective Equidistribution for some higher dimensional unipotent subgroups. So since I'm going to talk about some equidistribution results for unipotent subgroups, let me start the introduction by a special case of Ratner's celebrated theorem. So the very specific case that I would like to look at the beginning is the following. So I'll let G to be SL3R and gamma, just for simplicity, I will choose it to be co-compact lattice. You can choose it to be non-uniform if you like. Then you need to modify the later theorem a little bit, but I'll talk about that in detail later. And that acts to be G mod gamma. This is our ambient space where the dynamics will happens. And that's mu x to be the probability hard measure of this space. There is a natural and unique one. And the main role of dynamics today will be unipotent subgroups. And in this setting, I will choose this one parameter unipotent flow. It's like 1r r squared over 2 and 1r 0 1r and 0 0 1. It is the unipotent subgroup generated by this full Jordan block. Okay, and if you're familiar with sorry, if you're familiar with those groups, then you can see it is highly related to some indefinite quadratic forms. So if I let my quadratic forms to be 2xz minus y squared, a standard 2-1 form in three-dimensional, and I let my H to be the special orthogonal groups, the elements in 3 by 3 matrices preserve this quadratic form, then this unipotent elements we pick actually lies inside this smaller group. It preserves this indefinite quadratic forms. Okay, and under this setting, Ratner theorems goes like this. So for every for every initial point on my space, I look at this long unipotent orbit and I look at its time average on continuous function. Okay, I should say that's var phi, this phi in this theorem should be continuous and compactly supported. Okay, so you look at the time average for long unipotent start at this initial point x0, either it converged to the space average, or there are some obstructions that the h orbits of this initial point is periodic. So this unipotent flow or this unipotent orbit purely lies inside some lower dimensional algebraic subvariety. And okay, so this is the Ratner's theorem in this setting. And I should do a remark that if you like to pick your X to be non-compact, suppose you allow certain cost, then there is a third case that it might be trapped in the torus of on the cusp. But okay, just for simplicity, I will not discuss that in detail. And let me make a historical remark on this result. So for this unipotent flow, a topological version, a classification of orbit closure of such unipotent orbit was proved by Margulis and Danny Margulis before Ratner's work. And in fact, this is, if you choose your lattice to be SL3Z, the non-uniform one, this is exactly the setting where Margulis used to prove Oppenheim's conjecture. Okay, so let me move on. So I will also introduce a different formulation of the previous theorem. So let me introduce one more element in my group H. So I will let AT to be this diagonal element. So it's e to the t1, e to the minus t. And for this one, it is very easy to check that it preserves the previous standard indefinite quadratic form. So you multiply e to the t on x and e to the minus t on z, so it preserves this quadratic form. And it has a very close relation with the previous unipotent elements we pick. The unipotent elements we pick are exactly the unstable part of this diagonal element inside this smaller group H. So it is in other words, it is the horospherical subgroup of this AT inside this smaller group H. And okay, under those settings, we have the following theorem by Shah. It says that, okay, so now instead of looking at a long unipotent orbit, we pick an initial point and we look at a length 1 unipotent orbit, and we let AT, this diagonal flow, to push it. Because AT will expand this unipotent piece exponentially, this length 1 thing will get longer and longer in an exponential rate. And since my space is compact or finite volume, these things will fold up and wind around in the space. So there are two cases in this setting. Either this average will converge to the space average, as we see in the in the previous long unipotent orbit, or it is trapped in some lower dimensional algebraic objects. This H orbit of starting at this x0 is periodic, and it forms a lower dimensional submanifold. Okay, let me just say a quick remark on Shah's proof on this theorem. So Shah's proof is based on Ratner's theorem and the linearization methods by Danny Margulis and Shah. Okay, so that's all for this introduction part, and basically there are so now let me move on to the main objects or the main questions of this talk. I want to talk about something relates to polynomially effective equidistribution. So the question is whether we can get a rate of convergence in the previous settings or some more general settings. But sadly, it is not known in general, but there's some special cases are known. So for example, the most well-known case is the horospherical subgroups case. And the horospherical subgroup, I mean the horospherical subgroup inside this larger group. So let me just recall the definition. The definition for horospherical subgroup with respect to some diagonal flow in your group is defined to be the element in the subgroup so that it gets contracts if you flow backwards in time, or in other words, it is expanded if you flow in positive time. So in the previous setting, when G is SL3R, then its horospherical subgroup N will be the Heisenberg group. The group consists of 3x3 matrices, strictly upper triangular, and with 3 entries. And in this case, the question of rate of convergence of either the large unipotent orbit version or the size 1 and you push it by diagonal element version, those are well understood and has a polynomial rate. But the techniques for this horospherical case does not work for a smaller unipotent subgroup. For example, the previous one, that's my U is some unstable part of my diagonal flow, but not all of it. It is the unstable part in this smaller group H. And sadly, the techniques for horospherical subgroups does not work in here to provide the rate of convergence. Okay, so this is the main question I would like to discuss in this talk. And let me introduce a general setting. And okay, I should not assume that everyone is very familiar with every Lie theory words, but never mind. Let me just go through this slide and I'll provide more examples later. Okay, so basically in this talk, I will fix the following data. I have a group G and the lattice gamma, a smaller group H, a diagonal flow inside H, and a corresponding unipotent subgroup. And they're set to be as the following. So G is a connected semisimple linear Lie group, or you can say it's an identity component of real points of a semisimple real algebraic groups. If you're not familiar with it, G is SLN. And gamma is a lattice inside G, and in this talk, I will assume it to be arithmetic. And okay, from now on, I will not assume any compact, co-compact things for the lattice. It's just an arithmetic lattice. And through this talk, I will always let X to be G mod gamma. This is where the dynamics happens, and mu of X to be the unique probability Haar measure on my ambient space. Okay, and I have a smaller subgroup, a proper connected semisimple algebraic subgroup of G, and I assume it does not have any compact factor. And inside here, I will choose AT to be a flow of diagonalizable elements. It's generated by some semisimple elements in the Lie algebra, or if you like, in the setting of SLN, it is just a flow of diagonal matrices. And I'll assume that its projection to each simple factor of H is non-trivial. So this diagonal flow really sees all parts of H instead of just some part of it. And okay, now comes to our main character of this talk, the unipotent subgroup. The unipotent subgroups, I will pick it to be the unstable part of this diagonal element inside this smaller group H. Or in other words, it gets contracted when you flow backwards in time. If you conjugate this by a minus t u a t, it goes to identity when t goes to infinity, or you can say it gets expanded when t goes to, when you conjugate these things in positive time. And okay, this is the unstable part in H. And the key thing is it is not the horospherical subgroup of G. It is just its intersection with H, a lower dimensional object. Okay, and just to introduce this notation, I will use B1 of U to be a size 1 ball inside this unipotent subgroups. And I will define this to be as I pick a size 1 ball in the Lie algebra and then exponentiate it so that I get some ball in the unipotent subgroups. And okay, so the goal for today's talk will be studying the quantitative behaviors of the orbits of ATB1U. So I've picked a size 1 unipotent ball and I push it by this AT and it will get expanded exponentially when t goes to infinity. Okay, I said a lot of these serial words. Let's look at some examples. And it's good to just focus on these examples and several other examples in the next few slides. Okay, so the first slide of examples will provide us some one-dimensional unipotent subgroups. So in the first example, I can take G to be SL2C and H to be a smaller subgroup, the 2x2 matrices of real coefficient SL2R, or I can take the example to be kind of like a split version of example 1. G is SL2 times SL2, and H is a diagonally embedded SL2. Or I can take the previous example, G is SL3R, and H is the orthogonal subgroups preserving an indefinite quadratic form of signature 2, 1. And okay, in all those examples, this H is actually locally isomorphic to SL2. And in this case, we can let this diagonal element and unipotent element to be the corresponding part of our favorite one, AT to be the corresponding things to e to the t over 2, e to the negative t over 2, and UR to be this strictly upper triangular 2x2 matrices, 1R, 0, 1. I take the corresponding things in H. For example, in the previous example in the introduction, the e to the t1, e to the negative t inside that special orthogonal subgroup is the image of this AT. Okay, so those are examples where unipotent subgroups are one-dimensional. It's a unipotent flow. And let's look at some higher dimensional analog. So instead of 2x2 matrices, I can definitely look at d by d matrices with d greater or equal to 2. So I can look at G is SLDC and H is SLDR. Sorry. And I can also look at a split case of the previous one. G is SLD times SLD, and H is the diagonally embedded SLD. So those two are directly corresponds to the previous two example. Here I'm looking at 2x2 matrices. Here I'm looking at general d by d matrices. And I can also let G to be SLDR, and I look at like indefinite quadratic forms in higher dimensional. I can let H to be special orthogonal groups for some indefinite quadratic forms on RD, or I can not only look at the symmetric bilinear form, I can look at alternative bilinear form. I can let H to be the symplectic group. It preserves a symplectic form. Okay, and all those previous examples, or in most of the previous examples, H is simple. So let me give you an example where H is semisimple but not simple. So you can look at the tensor product of an m-dimensional space and an n-dimensional space. And the dimension for this tensor product will be m times n. So I can let my bigger group G to be SL m times n, and I let my smaller group to be SLN times SLM, that it acts on this tensor product via this tensor product. And okay, in all those examples, you can take the AT to be a regular diagonal flow in H. So if you don't know what's a regular diagonal flow in H, you can look at those SLD examples. And here it is just the eigenvalue for this diagonal elements are distinct. And again, I can let U will always be the unstable part for my picked diagonal flow inside H. Okay, so let me now pose some conditions. So I'll always use this math frac letter to denote Lie algebras for corresponding Lie groups. So in this setting, I have a larger group G and a smaller group H, and H is semisimple. So I can decompose my Lie algebra of this larger group into two pieces, H itself and a complement, where the complement is a representation of H. It is stable under H action. So I will call the above data consist of 5 elements irreducible if this complement is irreducible. And I will also call these things proximal if the largest eigenvalue of A1, or I should actually write add A1 on this complement is simple. or in other words, if you like, you can say the Lyapunov exponent of this flow on the complement. The top Lyapunov exponent for this flow on the complement is proximal, or it is the top Lyapunov exponent is simple. And the most important thing is that all the above examples satisfies this irreducible and proximal. So basically, this is conditions that is characterizing H to be sort of like a maximal proper semisimple subgroup inside G. And okay, I will discuss those conditions and later after I introduce the main theorem. But okay, before I state the main theorem, are there any questions or comments on the previous examples and the settings and the conditions I discussed? Okay, so now let me introduce the main theorem. So let's assume that the data G, gamma, H, AT, and the corresponding unipotent subgroup U satisfy irreducible and proximal. Then there exists a positive integer a bigger than 1 and kappa bigger than 0, depending only on the previous data, so that the following holds. For all initial point x0 in X and R large enough depending on the injectivity radius of x0 and t greater than r to the a, then one of the following is true. Well, the first is for every smooth compactly support functions, we have that this size 1 piece and expand average is close to the space average by a rate of r to the minus kappa. But okay, you need to pay a price of the Sobolev norm of your smooth function. Or there exists some other x inside my space x, so that the h orbit on this x is periodic with small volume. The volume is smaller or equal to r, and x0 is very close to this x. The distance between these two are t to the minus 1 over 8. So it says something roughly like this. Either such average equidistributed with a polynomial rate, or your initial point can be wellly approximated by some lower dimensional small submanifolds. And you can think about those periodic orbits of H as rational objects. So your initial point is wellly approximated by some rational objects, and it is not Diophantine. Okay, I just state the main theorem, so it's good to pause here to see if there's any questions and comments.
Yeah, so the two conditions here are not mutually exclusive, is that right?
Sorry, what do you mean by mutually
Yeah,
exclusive?
you have one. The theorem says that one of the following is true.
Yeah. It's so it can happen something like, so if you set your let's say if you set your t to be exactly r to the a, then they're not mutually exclusive. You can lie on the fairly large periodic orbits, and this fairly large periodic orbits, it's somehow nicely equidistributed in the space. Yeah, so they're not mutually exclusive. But okay, it's good to think about this as if 2 does not happen, then 1 happens. So if you start with a point that is not wellly approximable by those obstructions, then by those small obstructions, then you equidistribute it fast enough with a polynomial rate. Does this answer your question?
So can you explain how it compares with previous results?
Yeah, that's something I would like to do.
That's
Yeah.
probably in the next slides. Okay.
Yeah. Okay. That's the next two slides. So let me just give some remarks on these two conditions a little bit. So so I have two conditions, irreducible and proximal. And in fact, that if let me say it like this. So the proximal condition only appears in one place, but an important place in later proof. But in general, if your group is nice enough, suppose your edges are split and you choose a regular diagonal element, then it naturally follows from irreducible. Basically, in let's say in an algebraic closed or over complex number, every irreducible thing has highest weight is simple and the highest weight space is one-dimensional. But over the real numbers, these things might not happen. But when the group are split and you take a regular element, then this proximal condition always follows from irreducible condition. And also this proximality can be slightly weakened to some Schubert condition on the family of the H orbit of the fixed points of unipotent subgroups inside this complement R. But this will allow us to include certain cases where the groups comes from some complex Lie groups and you do a restriction of scalar. But so far I cannot eliminate this condition. And now let me give a brief summary of previous effective results. So I will mainly focus on settings that are closely related to my settings, and I will refer to the paper by Lindenstrauss and Mohammadi for a more thorough survey on previous other works. So in the closely related setting, in 2022, Lindenstrauss and Mohammadi proved an effective density result for G equals SL2C, H is SL2R, or G is SL2 times SL2, and H is diagonally embedded SL2. This is the first two examples in our setting. And later, with Zhu and Wang, they prove an effective equidistribution result for under this two setting. And in 2023, Lei Yang proved a case where G is SL3R and H is a singular SL2. So this SL2 is not the quadratic form SL2 we discussed before. It is the top left corner of your 3x3 matrices. And in this case, it is different from our conditions. The complement R is actually reducible. And I should also mention a closely related setting where people focus on random walks on homogeneous space. In 2024, Bernard He proved an effective equidistribution result for random walk on quotients of SL2R and SL2C. And later this year, Lindenstrauss, Mohammadi, Wang, and Yang proved the case where G is quasi-split of absolute rank 2 and H is a principal SL2R. So this case will cover, let me go to this slide, will cover all those three examples and several other cases. So those three are principal SL2 inside some quasi-split absolute rank 2 semisimple groups. And let me go back to this page. And later, also very recently, in the random walk setting, Bernard will prove an effective equidistribution result for random walk quotients of simple Lie groups. And I should also say that prior to all these works, in 2014, Lindenstrauss and Margulis proved an effective version of Oppenheim conjecture with polylog rate. So the work I discussed today, it's a generalization for this 2025 work by Lindenstrauss, Mohammadi, Wang, and Yang. And yeah, okay. So before I move on to the applications, are there any questions and comments? Okay, so now let me move to the application. And as the very first introductory examples are hinting, that one motivation of this work is try to get an effective version of Oppenheim conjecture in all dimensions. So here is an application. So for any dimension greater or equal to 3, and every that's for simplicity, let's take the indefinite quadratic form to be with algebraic entries and irrational. Then there exists some kappa depending on this quadratic form explicitly, so that the following holds. For all t large enough, depending also explicitly on the quadratic forms, and all real numbers lies inside the interval negative t to the kappa, there exists a primitive integer vector, non-zero, with size at most t, so that it's the value of this quadratic form on this vector is t to the minus kappa close to s. So basically, okay, Oppenheim conjecture says that the value of indefinite quadratic forms on integers or integer lattices is dense on the real line. And here it says that for elements of size at most t to the kappa, minus t to the kappa, t to the kappa, I can approximate those things efficiently. And how efficient it is by a polynomial rate. To get into an error of t to the minus kappa, I just need to search at most size t integer vectors. Okay, and this result is previously proved in the condition dimension greater or equal to 5 by Valters, Hill, and Margulis using some analytic number theory methods. And for d equals 3, this is proved by Lindenstrauss, Mohammadi, Wang and Yang in the same 2025 paper. And here we provide result works for all dimensions greater or equal to 3. Okay, so that's the first application on quadratic forms. Are there any questions or comments?
So algebraic quadratic form means that all coefficients are algebraic?
Yeah. All coefficient means are algebraic and it is irrational. Yeah.
But it's can you replace it by quadratic form with coefficients not sufficiently well approximable by something?
Yeah. You can replace it by the coefficients are Diophantine, and then you have this the similar result.
Okay, so in other words, you have it for almost all quadratic forms, not just for a countable set.
Yeah. So actually, the general thing is something like this. So it's like a dichotomy statement. Either it is dense in an efficient way, or it is wholly approximable by some rational quadratic form.
Mm-hmm.
Yeah.
Okay, nice.
Okay. Are there any other questions and comments? Okay, so now let me talk about the second application. So the second application is about dense lattice orbit on homogeneous variety. So now in this application, I will not look at something like continuous group X on G mod gamma. I will look at the dual version for that, which gamma X on G mod H. But okay, in this setting, there's one problem that there is no very canonical way to say what do we mean by a time average. So under this setting, or in this application I'm going to talk about, I will choose I will fix a Riemannian metric on my large group G and use this to measure like large balls inside H and large ball inside gamma. So H sub T will be the intersection of my smaller group with ball of radius T in this large group G, and gamma sub T will be gamma intersect with size T ball in G. Okay, and under this setting, Grodnik-Weiss proved the following results on asymptotes for dense lattice orbit on homogeneous variety. So suppose you look at so you pick an initial point y0 in G mod H, so that its gamma orbit is dense. Then for every compactly support continuous functions, the average along the lattice orbit is asymptotically the same as the average along the G orbit. So the first sum is some discrete points inside this homogeneous variety, and the second one is like a ball, and it is a continuous average on this homogeneous variety. And I should mention that the measure I use for the Haar measure on G should be compatible with the probability Haar measure on X, where X is G mod gamma. And actually, inside this theorem, you can ignore this 1 over mu H sub T. It is the volume of this gross ball in H. And this is the correct normalization in this setting. In fact, Grodnik-Weiss proved more than just these two average are asymptotically the same. They actually shows that with this normalization, it will converge to something. And that thing will be an integration of psi on G mod H, but the measure it integrate to depends on the initial point y0. And there is an explicit formula for that, but I will not discuss this in detail. So application for the previous main theorem is to provide an estimate of how well this asymptote is. So this is based on the joint work with Pratyush. So suppose your previous data satisfy this irreducible and proximal, or more precisely, I should say that there exists an AT inside H so that this data satisfy irreducible and proximal. Then in this setting, we provide a rate of convergence for the previous asymptote. So in the case where the rank of the larger group G is 1, we get an exponential rate of R of minus kappa. When G is when the rank of G is at least 2, then the error term is slightly worse. It is polynomials on T. And okay, all of this should start with an initial point that is Diophantine, so that in here we write this in the dual version, that the corresponding point in the space G mod gamma has a periodic H orbit with small volume. But okay, in the setting of gamma is arithmetic, you can actually give a rational structure, or you can embed G mod H in some linear subspace with rational structure and really say that your initial point is wholly approximated by rational vectors. Okay, and that's the second application. And are there any questions or comments? Okay, and let me just check. I have less than 10 minutes, right?
Okay, sorry, I had trouble unmuting myself. Yeah, I mean, you can have less than 10 minutes and then we can stop and then maybe we can have additional time for questions.
Okay.
So we are somewhat flexible.
Okay.
We should definitely finish at 2, which is 11 your time.
Okay.
And or earlier.
Okay, so let me try to give a sketch of the proof in approximately 10 minutes. And okay, so the general frame strategy or general framework follows from the seminal work by Lindenstrauss, Mohammadi, Wang and Yang. So the first piece of the framework is I need to introduce this random walk picture. So, okay, there might be some question like why I keep using this size 1 and expanding version instead of like a large unipotent orbit. So here is one advantage of using this size 1 and push version. So for this version, I can actually view this whole process as a random walk. So instead of looking at size 1 with a large proof, I can cut this time and view this as size 1 of unipotent with slightly smaller push. Or more precisely, because AT is expanding the unipotent in an exponential rate, if I multiply AT to B1U, AT1B1 of U, it is the same of a T1 plus T2 and a ball in unipotent of size of size 1 plus e to the minus T1. So with these things, we can cut this whole orbit into 3 phases where I cut T into T1 plus T2 plus T3, and ATB1 of U is approximately AT3B1 of U, AT2B1 of U, and AT1B of U. And also we can cut the middle phase into further smaller pieces of size L, where L is epsilon T2. And epsilon will be some small number, but it is absolute, depends on those data I pick. And okay, with this random walk picture, we cut this whole process into 3 phases. And the first phase is the initial dimension. Basically, you get using the arithmeticity of gamma, you can get initial dimension in the transverse direction R with some positive small coarse dimension. And then you can apply this random walk things to improve dimension in the transverse complement R. And at the end, this improvement will give you a dimension close to the dimension of the transverse direction R. And from that, we can utilize the spectral gap of X to obtain an equidistribution from large dimension. So let me just, okay, this is the general frameworks in Lindenstrauss, Mohammadi, Wang and Yang, and also this is the general frameworks for the main theorem I talked about today. So let me talk about some difference between my work with their work. So phase 3 is actually something that works in high generality. Basically, when you have a spectral gap and when you look at this kind of, and when you have a large enough dimension, then you can always get equidistribution with polynomial rate. And this argument can date back to the work of Venkatesh on sparse equidistribution. So phase 3 in general is not a problem. And let me first skip phase 2 and talk about a little bit about phase 1. So phase 1 is also not a big problem. So in their work, they utilizes the fact that their H is SL2R. And this simplifies some arguments here. But in general, phase 1 is not a big problem thanks to an effective closing lemma proved by Lindenstrauss, Margulis, Mohammadi, Shah, and Weiser for large unipotent balls. And we can make a transition between that effective closing lemma and to get an initial dimension here. And the main difficulties comes from phase 2, the improving dimension. And I will talk about this one in detail. So first, let me briefly talk about something relates to projection theorems used in the work of Lindenstrauss, Mohammadi, Wang and Yang. So in this case, H is SL2R. And the good thing for SL2R is that we know basically we know everything about its irreducible representation. So for such irreducible representation, let's just take a 5-dimensional one as an example. And let me just remark, this corresponds to the case of Oppenheim conjecture. The complement is a 5-dimensional irreducible representation. And in this case, under a suitable basis, you can write your UR in this strictly upper triangular matrices. And if you like, you can think about this irreducible representation as weight to be 4 to 0, negative to 4, and unipotent is sharing everything up. It's sharing everything to the expanding direction of your diagonal flow. And in general, we have the same picture. So if you let psi of r to be the moment curve, r square, r to the n, and okay, you normalize it by the factorial. And in the general irreducible representation of SL2R, you can write your unipotent elements as derivatives of this moment curve. So you have a very nice expressions for representation of SL2R. But okay, and in their paper, they utilizes the following nice but very hard, difficult projection theorem. So this is a projection theorem proved by Gang, Guo, and Wang, and it says the following. So for any compact sets in n-dimensional space, and you look at this type of projection. So you share up by your UR and you project to, let's say, the first few weights of your representation. Then this projection basically preserves the Hausdorff dimension. So so for almost every parameter R here, the Hausdorff dimension of the projection will be the minimum of the dimension K and the Hausdorff dimension of the original set. So your projection is a projection from n-dimensional space to k-dimensional space. It is a linear map, and the Hausdorff dimension cannot improve. And this is basically the optimal result. You didn't lose any Hausdorff dimension unless you have unless your Hausdorff dimension is too high, that is even larger than the projecting subspace you have. Okay, this is a feature in SL2 representation, but sadly, I don't know what happened. But sadly, in general, this is not true for irreducible representation. And in general, irreducible representation might have algebraic obstructions. So here is a typical example that this thing fails. So this corresponds to the 4-dimensional Oppenheim case. You let H to be SL22, which is locally isomorphic to SL2 times SL2, and G to be SL4. In this case, you can compute that the complement is a 9-dimensional representation, and it is the tensor product of a joint representation of SL2. So in this case, the weight space behaves as the pictures below. You have 4 here and 2 here, and 0, -2, and -4. So in this case, unipotent is sharing everything right and up. So if you want to, ideally, you want to have an optimal projection theorem, but sadly, this is not true. If you look at the weight space with weights larger or equal to 2, this corresponds to the top right corner. It is of 3-dimensional. And suppose your set is this one. This is a 3-dimensional linear set, linear subspace. But sadly, the unipotent can only move things up and right, and there is no chance for us to get these things. An optimal projection should project 3-dimensional things to 3-dimensional things, but sadly here you lose 1 dimension. Okay, I think I'm a bit running out of time, so let me just sketch a little bit about the solution for this. So the solution is try not to use optimal projection theorems. So the thing we try, so okay, let me just go to this slice directly. So the thing we try is that to gain dimension improvement purely from the top Lyapunov exponent. So we have a lot. So in a general representation, we have a lot of weights, and I don't pursue that from every of them I gain some dimension. I just want to have that on the top Lyapunov exponent or the largest eigenvalue, I can gain some dimension. So here is represent again. So K1 is so K1 is the dimension of R of lambda 1. Lambda 1 is your largest eigenvalue. So this projection provides something slightly larger than K1 over N amount of the dimension. And I also want to show that the other exponent doesn't lose too much things. So for this, I will show that the projections to other weight space will have the corresponding proportion of the Hausdorff dimension. And for these two pieces, basically, this is where one needs to use the proximal condition. So when it is proximal, then this distribution of the top Lyapunov exponent space will be nice. It is actually Holder regular. And for all the other spaces, they are not as regular as the top one, but still utilizing the irreducibility of my complement, one can prove a subcritical estimate, which basically means it doesn't lose too much. So this is the epsilon improvement. So in the epsilon improvement part, we utilize the theorem by the discretized projection theorem by Bourgain and later generalized by Wei-Kun He and Schmerking. So the key feature here is that you need that the directions you're projecting on the projected space has certain nice dimension. It satisfies a Kappa-Frostman type condition. And for the other things, the main ingredients are Braskamp-Leib inequality and the following actually interesting inequalities in irreducible representation. It states something for linear subspaces. So let me end by stating this theorem. So suppose you have an irreducible representation of H and you have two subspaces. It is irreducible, so it will tends to put these things apart. And this inequality says that you can put a W1 and W2 apart at this amount. So the intersection of HW1 with W2 is at most dimension of W1 times W2 over the dimension of the whole ambient space. And I should also mention that in the setting of a joint representation of simple Lie group, certain theorem is also independently proved by Bernard Hu. Okay, so I think I already run out of time, so let me just stop here and yeah, thank you.
Okay, well, we already see some hands clapping silently. Let me add my own hand. This was a very nice talk. We do have a few minutes for questions and discussions, so please ask whatever you want or make comments. Any questions?
Hi, could I ask a question?
Oh yeah, sure.
Could you say a little bit about how the submodularity inequality gets used in your strategy?
Sorry, which one?
This submodularity, yeah, this theorem.
So it is. So basically, you can think about this as the Braskamp-Leib tells you something that if you have a correct subcritical estimate for linear stuff, then in general you should get uh, correct subcritical bounds for entropy, and basically that is how it's used. So it is okay, but the version I wrote here it's not exactly the version that I use to apply Braskamp-Leib inequality. The version I use is in fact an average version for this, and so But okay, it is roughly the same as this one. But the thing, okay, so for this one, if you look at the H that satisfies this inequality, it will form a Zariski open dense subset depends on W1 and W2. And the version I use will be something like, in average, this thing holds. And there is a Zariski open dense subset for that thing to be whole, but it does not depend on W2. It purely depends on W1. And that is the thing that I use to as an input to Braskamp-Leib inequality, and Braskamp-Leib inequality give us a bound for entropy. Yeah. Does this answer the question?
So this Braskamp-Leib inequality roughly says that the measure of a box is somehow the product of the measures of its projections. Is that roughly?
Yeah. That's roughly what it says. Yeah.
And you get some gain from the top exponent and no loss from the others.
Yes.
But I'm not quite sure. I'm not quite sure where this submodularity comes into the picture exactly.
Okay. So actually, it's like this. So previously, yeah, what you said about Braskamp-Leib is perfectly correct. But the problem is that for those subspaces, they are not exactly transverse. So basically, the thing you get is like, so let me say, so write this down. So basically, what you want is, so okay, I'll write something like this. W1 over dimension of V. So basically, sorry, I should put this in the exponent since I'm using Covery number now. So this is the no loss things that we want. And ideally, if you can find like some H1, H2, H3, all the things that those things are transverse, then it is exactly what you said, that the measure of product of those things is larger than the measure of these things. But the sad thing is that usually you don't get transverse things, and you need to study these things carefully, and this is where this submodularity inequality comes into the picture.
I see. Thanks.
Yeah.
I think I understand. Thanks.
Yeah. Oh, and in fact, actually, the previous examples here, I think, yeah, this one, I think if you compute these things, then if you look at 3 copies of this 3-dimensional things, you move it with H, then they will always just generate an 8-dimensional things. They will not generate the whole space. Yeah. And that's why we need such submodularity inequality. Yeah.
Thanks. Yeah, thanks.
Okay. Other questions? Comments? All right. So let's thank Zoe again. Another round of applause. It was very nice talk. So the preprint is already available, right?
Sorry?
So it's already posted?
Yeah.
Should look at it. Okay, well, thank you.
Thank you.
And I hope we'll meet again.
Yeah.
Later.